Hey guys, welcome to another A-Level Maths revision video. Today we're taking a look at the very final chapter now in our first year material of stats. So, hypothesis testing can be a chapter that a lot of students don't enjoy. But hopefully after this video here, you won't find it too bad. Okay, so let's take a look at some revision. So this first question here, pretty standard exam type question. Just finding the critical region of the test and then the actual significance level. So, for this question here, I'd advise using your binomial tables. You can do it using trial and error with your calculator, but I think just getting on with it using the tables is a bit of a nicer way to do it. So what we're told here is we have a random variable which follows this distribution, binomial distribution, n is 20, and then p, which we're told in the question is 0.4. Okay. So for part A, using a 5% significance level, can we find the critical region? So in this case here, with it being a two-tailed test, we have the lower tail and we have the upper tail. Okay, so we've got two cases we have to consider here. So what I'm looking for here now is the probability that x is less than or equal. So let's just say, I think the textbook uses C1. So let's just say C1. Okay. And the probability that x is also less than or equal to C2 for now. Okay. And what we're looking for here, so with it being a 5% significance level, we're going to compare this to 0.025. So just be very, very careful. It's not 0.05, 0.025, because it's 5%. You divide it by 2, because we've got both tails, okay, to consider. So what I'm looking for here is the case where I get the first probability where it's greater than 0.025, and then for this one here, this one will be less than 0.025. Okay. So what's this going to look like? Well, to do this, use the table. So, in your case, you'll have to go through your formula book. So, n is 20. So, get to the one where it's n is 20. So, like you can see here. P. So, in our case, we're using the fact that p is 0.4. So, we're down this column here. And how do we do this? Well, go down the column. So, we want the first one where it's greater than 0.025. Okay. So whereas the first one where it's greater than 0.025, well, 0.000, so it's not that one. It's not this one, 0.0005. It's not the next one. And it's not this one. So my first one has to be this 0.0510, okay? That's the first one, 0.0510. That's greater than 0.025. And what's the x that corresponds to that? Well, if you go along that row, that's 4, okay? So I just scribble that out. That's probably that x is less than or equal to 4, okay? That gives us 0.0510, and that's greater than 0.025. So all you do then is you look for the first one that was before it, if that makes sense. So in that case, just go one back, so it has to be this 0.0160. Okay? 0.0160. So it's the first one before we're greater than it, okay? And what value corresponds to that? Well, it's just 4 minus 1. Which is 3, and again you can test that if you go along the row, 0.0160, we get 3 there, okay? So, for this one here now, we consider both of these values, and we want the one that's closest to 0.25, so if we ask this as a rhetorical question, closest to 0.025, well, consider both your values, and which one's closer? Well, it's this one here, 0.0160, so what we say then is that the critical value for this tail is this value here, so it's 3. So critical value is x equals 3. Okay. We're now going to repeat the same process for the upper tail. It's just a little bit trickier. Nothing too bad, but again, you know, it's a slightly bit more complicated. So now consider the upper tail. Now consider the upper tail. Okay, same idea here, but this time, instead of it being less than or equal, we're looking for greater than or equal to. So, if we just say x is greater than or equal, let's just use u this time, so u1, and we'll use u2. Okay, so, what I'm looking for now, again down the same column here, we're working from this end. So we start along technically this row here, but work up the column. Now what I'm looking for is the first value where it's going to be on the other end of the tail, if that makes sense. So 1 minus this 0.025, so that would give me, what would that give me? That would give me 1 minus 0.025, so 0.975. Okay. So I'm looking for here now the first time where we go past that value. Okay. And if you look here, we've got 1, 1, 1, 0.9997, so it's not that. It's not this here, 9984. It's not 9935. It's not even the 9790 because we need 975. So this next one here is the key value, 0.9435. Okay, so that would correspond to the fact that we've gone greater than it. Okay, so what we're doing here is 1 minus that corresponding probability. So what's that value? 9435. So that's 11. But remember, because this is an upper tail test, or at the upper tail region here, because we're doing greater than or equal to, we've got to do 1 minus that probability. So this is 1 minus the probability here. So that corresponds to 11. So this has to be 12. So this has to be 11 here. Okay, so this is a little bit tricky, and I don't think I explained it particularly well. But it comes with practice, and you will get used to this method. Okay, so that's the first one. Then you're looking for the one above it here. This is the one previous, so which one comes before it? So again, like we did here, it's the first one that doesn't satisfy it. So where was we? 9435. So it's got to be this one here, this 9790. Okay, so that's 12. So that's 1 minus the probability that x is less than or equal to 12. So here it's just 1 extra, so that's 13. Okay, so hopefully that makes sense. And then here, just work out your corresponding probability. So this is 1 minus 0.979, like we just read off the table. Oops, I'm not even writing the right number. 1 minus 0.979. Okay, and what does that give us? That gives us 0.0210. Like we said, this is less than 0.025. And this one here, this is 1 minus 0.9435. And this gives us the first one greater than 0.025. Okay, that's greater than 0.025. So in this case, again, consider both of these numbers, and we're going to see which one's closest to 0.025. So again, closest to 0.025. Well, in this case, that would be the one for 13 here, this 0.0210. So what we say is that the critical value, we'll just call it C dot V, that's equal to, that gives us x equals 13. Okay, so the critical region then, so the critical region, so this is the key part now, the answer to the question. How do we define the critical region? Well, we're saying x equals 3 for this tail, but remember this tail we're looking at less than or equal. Okay, so the lower tail is x less than or equal to 3. Okay, so we just do the critical region down here in the bottom corner. So x less than or equal to 3. And then if you consider the upper tail, we picked x equals 13, so it's everything greater than or equal to 13. Like so. Okay, so them are our two, well, that's our critical region there. Okay, so that's your lower tail, and that's your upper tail. So it's quite a long method to explain, doing it by hand like this and trying to do it as I explained it. But with practice, you will kind of speed through these questions. You will get very kind of confident with them. So then finally for part B here, if we write down the actual significance level of the test, that is just simply the two values that you essentially picked out. So we picked this one, because that was the closest. So it's the two closest values added together. It's really easy. So whichever one did we pick out? We picked the 0.016, didn't we? Like that. Okay, so if you just add these together, so actual significance level, and just add these together, so 0.016 plus 0.021, and that gives us 0.035. okay, which is approximately 3.7% there. Okay, so like you can see, the last part's dead easy. The two numbers that we picked out, add them together. Okay, well that's that first question done. Now we're going to take a look at some hypothesis testing. So the most important thing with any of these hypothesis testing questions is just essentially diagnosing whether it's a one-tailed test or a two-tailed test. Okay, that's the most important thing here because it defines how the test is operated. So for question 10 here, let's just see if we can figure out which way it goes. Is it a one-tailed or is it a two-tailed? So we've got a certain blood test, blah, blah, blah. So this is the key part here where you've got the manufacturer's claim, essentially. So the manufacturer suggests that a cheaper test will have the same probability of success. So that's the key fact. They're not saying that it'll be better. They're not saying it'll be worse. They're just saying it'll be the same. So if it's the same, what we're actually doing here is we're defining that as being a two-tailed test. It's less than or equal. Or it's not equal to, sorry. So I'll stop talking because I keep saying the wrong thing. So the probability is 0.96. They told us that in the first line. So your H1, sorry, it's not less than or equal. It's just not equal to like that. Okay, so it's two-tailed test. Two-tailed test. If we just quickly define as well, so we let X basically be the number of patients correctly diagnosed. So the number of patients correctly diagnosed. And if we also let P be the probability that a patient is correctly diagnosed. Okay. So here now, we've got our hypotheses. So that's the first thing. Always write down your hypotheses. It's the first part to any hypothesis test. So with this being a two-tailed test now, it's a little bit more complicated than a one-tailed test, for example, because we need to decide which way the inequality goes that we test. Okay, so let's just define this distribution. So X is a binomial distribution. What's N? Well, we're told in the question there's 75 patients, so N is 75. And what's P? Well, P is just what we've got in the question as well, 0.96. So we've got our distribution here. So what we need to do now is work out the mean, the expected value. So remember, for a binomial distribution, this is in your formula books, you don't have to memorize it, but it's not too tricky. The expected value is just simply N times P. So NP, which in this case is 75 times 0.96. So if you do that on your calculator, that gives you 72. Okay. Now, what we do here is we consider the evidence that we've got. So that's this line at the bottom here, 63 of the patients are correctly diagnosed. And we consider that. So is that 63 greater or smaller than the expected value? If it's smaller, then we test the inequality as being less than or equal. If it's greater, then it's greater than or equal. So 63 is less than 72, obviously. So testing now less than or equal. So probably that X is less than or equal. And you test the evidence, 63. Okay? Like so. And then at this stage here, just use your calculator, use your graphical calculator. Tables, if you really want, but I'd just use your calculator. You are supposed to really be using them. So this gives you 0.00417. We compare this now to our significance level. Well, two-tailed test, so again, be careful. We don't compare it to 10%, we're comparing this to 5% now. So is this greater or smaller than 0.05? This is quite clearly smaller than 0.05. Okay, so in that case, reject H0, and then let's just write a little conclusion. So we reject H0, so that means we've got evidence at the 10% significance level. So evidence at the 10% significance level to suggest that the new test does not have the same probability. Okay, I'm just going to shorthand that as prob. I can't be bothered, but yeah. Okay, so always give your give it a little bit of a conclusion at the end, just to basically summarise everything that we've done and just, you know, essentially let the reader know what's going on. Okay, but that's a two-tailed test there. Take a look at this question here now. So again, these questions are always packed with information. Another key factor is just pulling out the things that we do need. So first, let's have a go now. Can we basically identify whether it's one-tailed or two-tailed? So, looking at our question here, so I don't know how you pronounce that name. Is it May? Mai? I don't know. We'll call her May. Basically, she commutes to work, blah, blah, blah. So here's the key fact now on the end of this line. So she thinks that the service will be late more often. So that's the key thing, more often. If you're looking at something either being more often, or more common, or less common, for example, so in this case we've got more common, then this is a one-tailed test. Okay, we're being quite specific in our test. So if we just quickly define our hypothesis, so H naught, so we're saying 20% of the time, so if we write that as a decimal, so that's P equals 0.2, and then H1, so again, P, the probability, she thinks it's going to be late more often, so that's P greater than 0.2. Okay, the higher that probability, the more often it's late. So now we need to define the distribution. So really I should define what X is in my probability, but I'm just going to leave it out for the sake of time. What's my N in this case? Well, read the question carefully here. She commutes to work 5 days a week, and obviously she does 2 journeys, going there and going back, I assume. So that's 5 times 2. Okay, so be very careful. It's not 5, it's 5 times 2, giving you 10. And the P is obviously what we've got in the question, 0.2. So what we need to do now is set up basically our testing value here, what will give us our test statistic. Well, for a one-tailed test, nice and easy, you just test whatever this is. So if this is greater than, we're testing greater than or equal to. If it's less than, here, less than or equal to. Nice and easy, you don't have to work out the expected value for a one-tailed test. So we're testing the probability that X is greater than or equal, and what's this value? Always use your evidence in the question. In the first week of the new service, the train is late 3 times. So this is X greater than or equal to 3. Remember, if you've got a probability like this, where it's greater than or equal, we do 1 minus the probability that X is less than or equal to 1 minus this, so 2. And then at this stage here, you can use tables. I'll just use your calculator to work out this here. So this is 1 minus 0.6778. If you work that out, you get 0.3222. Okay. We compare this now to our significance level, which is 5%. So so one-tailed test, we don't divide it by 2. We do compare it to this now. So we compare to 0.05. Well, this is larger than 0.05. So in this case, we accept H naught. Okay, so accept H naught. So we accept H naught here. And again, just give you a little bit of a conclusion. So we'd say there's no evidence at the 5% significance level significance level to suggest that the trains are late more often. If you struggle to give the conclusion, just use the hypothesis to help you, right? We're testing whether the train probability of it being late here is basically the same, 0.2, or whether it's it's late more often, it's larger than 0.2. Well, if we're accepting H naught, we're saying that there's not really any change in the probability. So in this case, we're suggesting that the trains, there's no evidence that they are late more often. So suggest the trains are late more often. Okay. So that's that question done. But like say 7 marks these questions, they're not too bad. Just get used to the method, you'll be alright. So another hypothesis testing questionnaire, so we've got quite a few in. Again, have a quick check, see if you can identify whether it's a one-tailed test or a two-tailed test for this one. So hopefully you've kind of figured it out. For this test here, we actually have a two-tailed test. And the reason for that is because we're testing whether or not the evidence is that the proportion of women using this is 0.5. So we're not testing whether it's larger than 0.5, we're not testing whether it's less than 0.5, we're just testing whether it is that. Okay, so think of these as quite the boring test, I guess. You know, there's not much to them. So H0, so that's P, is equal to the probability 0.5. And then we're not checking whether it's larger or smaller, just whether it, you know, it is that. So this is not equal to 0.5. So then my hypotheses. Now we need to basically give our distribution. So X is a binomial distribution. So what's N in this case? Well, that's the random survey of 20 women, so 20. And what's our P here? Well, our P is just what we've got in the question, 0.5. So now, with this being a two-tailed test, remember you need the expected value. So if I call it EV, so expected value, that's N times P, where N is 20, and P is a half. So 20 times a half, that just gives us 10. Okay. So now we compare the evidence to the expected value. So you've just got to be very, very careful here. This is one of those kind of trick questions. So 12 said they did not use the powder, but what we're actually testing here whether they did use the powder. So we're not. Our evidence isn't actually 12. Our evidence is 20 minus 12, so 8. So you've just got to be very, very careful for that. So what we're checking now is whether 8 is bigger or smaller than 10, which quite clearly 8 is less than 10. So in that case, we're testing the probability that X is less than or equal to 8. Okay. Work this out in your calculator using N is 20, P is 0.5, and what you should get here is 0.2517. Two-tailed test. So if it's a 5% significance level, we're comparing 0.2517 to 0.025. So quite clearly, this is bigger than 0.025. So in that case, when this is bigger, and then we accept. So accept H0. No evidence or insufficient evidence. At 5% significance level to suggest the claim is incorrect. Okay, so like you can see, these summaries are pretty standard. Just get them done. They're a bit boring, but even when you're practicing these questions, it's a very good habit to have. Always try and do them if you can. Okay. And then moving on to this very last question here, we've just got some definitions. So I wouldn't worry too much about memorising these, but I've included them just because you are kind of expected to know them. Out of the three of these definitions, I think the hypothesis test is technically the hardest because it has the longest definition, and I think a critical value and acceptance region are fairly obvious. So let's just see if we can give these definitions here. So what's a hypothesis test? Well, first let's just define what a hypothesis is. So I'm just going to write this down. This is the textbook definition. So it doesn't have to be the exact textbook definition, as long as you can give something along these lines. So this is a statement made about, so I can't even write, made about the value of a population parameter So now let's actually define what a hypothesis test is. So we've defined what a hypothesis is. So in that case, hypothesis test uses a sample or an experiment to determine whether or not we actually reject the hypothesis. So whether or not to reject the hypothesis. Okay, that's simply all you kind of got to jot there. So what I do, define basically what the definition of a hypothesis is, and then actually define what a test is for it. Okay, critical value, much easier. So remember, the critical value is just the first value that's within the critical region, so not too bad. So the critical value is the first value to fall within the critical region. So that's quite a nice easy one. And then finally, an acceptance region. Again, nice and easy here. What is an acceptance region? So the acceptance region is just the region where we actually accept the null hypothesis. So that's the key fact, it's the null hypothesis. So the acceptance region is the region where we accept the null hypothesis. Okay, and that's it. Definition is done, as dull as they are. So that actually brings us to the end of this video. I don't think it's been too long, I hope, but I hope it has helped. If there's anything that's unclear, because this is probably the trickiest part of the Year 1 material, just let me know down below. I'll try my best to make it a bit clearer. But yeah, cheers.